Hi there and welcome to this video for Senior Physics on electrostatics and electricity. In this video we're going to explore the Van de Graaf generator. So basically a Van de Graaf generator, as you can see in the picture here, is one that can produce huge amounts of negative or positive charge on a metal dome by the addition or removal of electrons. It basically uses the triboelectric series by rubbing off or putting on electrons onto a rubber belt. So as a result, we get that classic photo where often you put your hand onto the Van de Graaf, and the result is that due to repulsion, your hair stands on end. But how does it work? So what we're going to do, we're going to go over into the lab now, and I'm going to run through basically how a Van de Graaf generator works and explore some of the properties. So come with me and we'll go and have a look at that Van de Graaf generator. Hi there and welcome to the lab. So basically what we're going to do is run down the principles behind the Van de Graaf generator. So as you can see here, I've got a Van de Graaf generator which is then linked to a power pack. Now the Van de Graaf generator, as we said, is going to induce electrical charge. Now the Van de Graaf generator itself was invented by American physicist Robert J. Van de Graaf in 1929. And as I said, a Van de Graaf generator is an electrostatic generator which uses a moving belt to accumulate electric charge on a hollow metal globe which is on an insulated column, thus producing very high electric potentials. Now as you can see, this is our globe and this is our insulated column. On the inside here, basically what we've got is a rubber band, and we've got rollers which would cause the rubber band to move. Now basically, as I stated, it produces low currents but large amounts of charge. Now the charge difference or potential difference achieved in these Van de Graaf generators can reach in some cases up to about 5 megavolts. But this tabletop version probably will go around about 100,000 volts. So that's 100,000 joules per coulomb, which is generated on the top. And that is due to the energy which is produced due to the electrons repelling each other. And more on that later on in the course. So we can get enough energy which is generated, which will actually produce a spark. So let's turn it on and see how spark is going to be generated, and then we'll come back and explain how it all works. So as I stated, I've got a motor here. The motor is going to drive the belt. So I'm going to turn the light on, and you can hopefully see the belt starts moving. Okay, now as the belt starts moving, what's going to happen is we're going to put charge onto the dome. Now I'm not going to get too close to it because obviously the energy which is going to be generated will be earthed by me, which means that I will then get the shock. But I can show that using a globe over here. Now basically what I've got is just a globe. This globe here is now attached to the ground. It's been earthed. And when we get it close to the globe, we can see a really good spark which is generated in each case. Hopefully you should be able to see that. We'll zoom in a bit closer. Okay, we'll take it back out again. And we'll switch it off. We're just going to earth it. Okay, so how does this work? How does the Van de Graaf generator work with respect to generating these electrons? So what I'm going to do is I'm going to take off the globe. So we'll take the globe off now, and you can see the main process behind. Now, the globe itself is literally going to be the last point of whether we get an increase in electrons or a deficiency in electrons. Obviously, if there's a deficiency in electrons, it's going to be positively charged. An increase in electrons will mean it's negatively charged. And depending how the rollers are set up and the machine is set up, it will basically run on the principle of having electrons being rubbed off or electrons being put on. And it's all down to the triboelectric series that we talked about earlier. Now, as I said, the Van de Graaf generator consists of a belt of rubber, which is running over two rollers. There's one roller here, and there's one roller here. Now, these will be of differing materials, and as a result, the differing materials will allow, using the triboelectric effect, electrons to be rubbed off or put on, depending on where they sit on that series. At the top here, we've got an electrode here, and we've got an electrode here. So what I'm going to do is I'm just going to zoom in with the camera and allow you to actually see those electrodes. So you can see the electrode, which is just acting here, and then there's another one down the bottom. And here's the electrode down on the bottom here. Okay, so we've got these two electrodes, and what happens is as the electrons are rubbed off or put on, the result is that these will be our conduits through which those electrons are going to flow. So this comb here will be attached to the airspace, which is going to then be linked to the electrical dome. So you can see that it's linked through here and will pass up through this tube here. So the method of charging is based, as I say, on the triboelectric effect, where simple contact of materials causes the transfer of electrons from one material to the other. So the rubber belt will become negatively charged as it passes over an acrylic glass roller, whereas it will become positively charged when it goes in the other area. The belt carries away the negative charge on its inner surface, while the upper roller accumulates positive charge. The result is that there's a strong electric field surrounding that upper roller, which induces a very high electric field near the points of the comb here. So, at these points, the field becomes high enough to ionize the air particles, air molecules, which are inside here. The electrons that are attracted to the outside of the belt will then go onto the ions and produce, get the positive ions forming onto this electrode. At the comb, the ions are neutralized with the electrons, thus leaving the comb and the outer shell with fewer electrons, and the result is they become positively charged. As a result, electrostatic induction has been produced. Now, that's all well and good. Literally all we need to understand, though, is that we've got electrons which are moving off, causes ionization of the air, which draws either electrons away from the globe or onto the globe. So the question then is, how does it affect us normally? Well, you've all seen the old hair going up on its end. Why does that happen? Well, that's basically because as we touch the globe, the result is that we then become a conduit of a flow of electrons, either towards or away, depending on whether we've got a positive charge up here or a negative charge. If we've got a negative charge, then the result is the body is then used for the electrons to move away, so we get negative electrons on our hair. Likewise, if this is set up to be positively charged, they're going to go in the opposite direction, leaving positive ends on your hair. The repulsion of either the negative or the positive charges on your hair results in the hair standing up because they want to repel. And in a three-dimensional space, what they cause is an actual sphere, which is going to be generated. Okay, so let's have a look at the Van de Graaf working again, and I'll try and demonstrate a few more things with that Van de Graaf. Okay, so basically I've got my Van de Graaf all set up. Now what I'm going to do is, this is basically just an acrylic piece of material. It's going to act like our hair. What I'm going to do is I'm going to stick it in a hole at the top of the Van de Graaf. And as I stick it in the hole, we're going to see the effect just like we would have using normal hair. So we'll stick it in there, and what it will do is show the flow of the charge. Now, obviously, what we're looking for is these to start sticking up. They're going to repel from each other due to either that positive or negative charge and form or move away as far as they possibly can. So we'll set up the Van de Graaff generator, get it running, and then we'll look at this in a little bit more detail. Okay, so you can see already that the acrylic is now standing up. I'll zoom in for you. So now they're standing up on their own. And the reason is we've got repulsion up here. I'm not going to get too close because you can see already that my hand is having an effect on the actual acrylic. So I can actually move it due to me either being positive or negatively charged. Okay? Because this works on a positive machine, what's happening is I've got more electrons. So electrons from me are going to want to jump. And we'll see them moving. There is attraction between me and the air. But look what's happened when I put my globe onto my Van de Graaff. Okay? So what I'm going to do is just grab my globe here, and I'm going to put it close. Now watch what happens, because what's going to happen is I'm going to earth whatever's on that globe. Watch what happens to the strands. Now obviously we get a nice electric shock, but as the electric shock is occurring, this is earthing. This is giving a different place for the electrons to go. As a result, there's less repulsion in the acrylic hair at the top, and the result is they drop down because there's no repulsion. Watch it again. You see it drop. See it drop. The reason why it stays up in this case is because it's keeping on generating. So it's still got electrons which are continually moving. But watch what happens when I switch it off. As soon as you might have heard that little click there, as soon as I clicked it in, the result is they dropped straight away. Why? Because we'd earthed all the electrons, everything was neutral, and then the result was there was no repulsion which was generated whatsoever from those charges. Let's look at it one more time. So we're up in the air, nicely charged up. I'll switch it off. Suddenly it instantly drops back to normal due to that lack of repulsion. So basically what can we assess from this? Well, the Van de Graaff generator is a really good device for showing the movement of electrical charge. We can generate huge amounts of electrical charge on this and see the effects of that charge moving from one place to the next. Okay, look, we're going to go back to the video now, and what I'll try and do is explain exactly what happened with respect to the hair. All right, I'll see you in a few minutes. Okay, so we get the idea that the hair basically is going to increase in volume. Basically, it's going to form a sphere. Now, the sphere, as I stated, was due to electrons being moved either away or from the tips. What we get is either a highly negative or a highly positive charge at the tips. Because they repel, they become equidistant from each other. Now, what will happen is you'll get one strand of hair which will move away, and it will keep repelling until it's repelled from the other side from another hair. The overall effect is that we get this equal spacing of each of the hairs, and the result is that we get this sphere which is generated. Now, also on this post, I put up a video from Bill Nye from the Disney Channel, who also explains about static electricity. So it might be a good idea to watch that video. He puts a nice little bit of animation in to explain how that hair moves away. Also, I put up a video of our class, and we've noticed that by making sure that people were not touching the floor, so they were not earthing, we got a long line of students, and they all held hands. One put their hand on the Van de Graaff generator, and the result is all of their hair went up. Why was that? Well, it was again down to repulsion, which was occurring between each of their bodies. Okay, well, I hope this has been insightful with respect to understanding the Van de Graaff generator. Thank you for watching, and I look forward to you meeting me again. Bye for now.